Okay. Hello, everybody. So my name is Nicholas Matsakis, and I'm going to be speaking about the Rust programming language. And it's something I work on. I've been working on it for about 6 years. I work on the compiler and the language design and the type system and so on. And I think I figured I would start with kind of the two questions that most people want to know when they're coming to learn about Rust. You know, what is it, and why would I even care? I have enough programming languages to choose from, right? The kind of shortest way to say what Rust is all about is that you should be able to write really high-level, nice code, but get the low-level performance that you might get from C++ or C or something like that. And the goal is to kind of eliminate this trade-off that you normally have to have. So a lot of times people would like to use C++ because they want the kind of control over the machine. They want to be able to have a tight allocation on memory or no, it's not going to be any surprise latency gaps from the garbage collector. Or maybe they just want flexibility. They want to run on an obscure architecture or plug into another virtual machine, like Ruby or Python or whatever. But it comes with a certain cost, right? All these horrible bugs, these sort of legendary problems that maybe you've been lucky enough never to have to deal with, but maybe not, I don't know. And so, for the most part, the world has solved these problems by adopting a garbage collector and a runtime. And so most languages these days have a garbage collector. And that means you give up some of this control and some of this flexibility, because now you have to have this runtime, and it decides when memory is allocated, when memory is freed, and so forth. But in exchange, you don't have to worry about a lot of those bugs. But not all of those bugs, actually. Right? So if you've written parallel programs in Java or something like this, or in Go even, you may have experienced data races, which are a really difficult, probably the most difficult thing to track down. And so Rust wanted to take a different approach. Right? We wanted a language that retained the control and flexibility, but solves the bugs. And how do we do that? We do it with a type system, a static type system, which means the compiler will reject your code if it thinks you might have bugs like these, right? And a lot of times when I talk about a type system, I think people get a nervous feeling. They've had bad experiences, you know. It sort of sounds like your parents saying, finish your plate and eat all your food, and you're thinking to yourself, I just want to ship some code. I have a deadline tomorrow. I don't need to mess with the compiler, which is like telling me it won't run my program. But this is not how I look at it, okay? I don't look at it like this kind of spinach. It is spinach, but it's Popeye spinach, right? It's something that makes you able to do more than you could do before, because you can rely on the type system as your ally. And let me explain what I mean by an example. This is from a blog post from a Boston company that uses Rust. And they were explaining how they had a sequential for loop. And they thought, there's no reason I can't run this in parallel. I'd like to run this in parallel. So they dropped in, I'll show you later, that's just one line of code in Rust to convert. And it didn't work. It didn't compile. And that was a good thing, because it turned out they were wrong. They couldn't do that safely in parallel. There were some subtle problems, and the compiler detected them, reported an error, and then they fixed the problems, and then it worked. Right? And that's what you want. This actually happens to me on a pretty regular basis. That I go in, I try to parallelize some code, and there's this little speed bump along the way where I fix a few compilation errors. But once I'm done, everything works, right? Instead of it runs right away, but then down the line it crashes here, it crashes there, it crashes when the customer's trying to use it, and and I'm never really sure if I've got all the bugs or not. So let me give you another example where just to give you a kind of visceral feeling, because the other part of Rust that I'd like to sell, besides that we prevent bugs, is that we still let you write high-level, nice code and give you the performance you're looking for. Right? So this is an example of some Ruby code. This is the definition of the blank method, which tests if a string is all white space. I don't know if it still is. It was at some point, the actual definition in Ruby. You can see it uses a regular expression. And it turns out that this could be a performance bottleneck in Ruby on Rails installations. And the reason was, every time a request came in, they would check if the URL is a blank string. So they called this function a lot. Right? And it turned out it was high in the profiles, And so somebody said, let's rewrite it in C. And now it'll be faster, right? And it's a little bit longer. It's not that hard if you know C, but it's still, it's got some random pointers. They're running all over the place. This could introduce a security vulnerability easily, right? Plus it has all this Unicode, I don't know. But it was a lot faster. And if you run Ruby on Rails, you probably should use this gem by Sam Saffron. And so that's good. And for a long time, this was a thing. Now, Sam later was exploring Rust, and he said, let's rewrite that same function, but in Rust. Right? So we remember this was the performance we had. This is what he wrote in Rust. And the idea was, this is going to be my first draft. Then I'll go through and make it ugly and fast. Right? I'll start by writing this high-level thing. And here we get a string slice, which is a subset of a string. And we use this iterator to go over every character in a Unicode-aware fashion. And then we invoke this method, which says, for every character, call this closure and see if it's white space. And this is all stuff that you may be used to using, but you're also used to it carrying a runtime cost, right? And in fact, though, when we measure the performance of this function, it's exactly the same as C, right? Or even a little faster, though I think that's measurement error. But the point is, the compiler is able to compile that down and produce the assembly that is equivalent to that big thing of C code we saw. And the reason it does that is it builds on a lot of cool ideas, mostly pioneered by C++, called zero-cost abstractions. And there basically means we design the language in such a way that a compiler can be kind of guaranteed to optimize it if you code in a certain style. And it doesn't require heroic, super complicated optimizations on the part of the compiler either. It doesn't have to do whole program analysis and so on. So it's much more reliable. And you can build up, right? This was the example I just said with an iterator. But we'll see later, we can also do things like parallel iteration, right? Just by putting this one method, par iter, now we can take a bunch of work and run it on a garbage collected runtime with different, sorry, not a garbage collected, a work stealing runtime with different threads and so forth, and get efficient execution. And this is pretty cool, right? This is really powerful stuff. And having these libraries, the only thing is, traditionally, if you were working in a systems language like C, there are a lot of libraries out there, but using them is a real pain in the neck, right? You don't tend to reuse much code because you have to go get some makefile, figure out why it doesn't build on your flavor of Linux or Mac or whatever, and do a bunch of work. But we make that pretty easy. So that's another thing that Rust offers, is a nice package manager, very similar to gems, Ruby gems and so on, where you can just add one line of code and it will download and configure and build everything for you and make it easy to use other people's libraries. Right? So that's kind of my what I call the hard sell for Rust, right? It's kind of me trying to convince you why you should use it. And basically it comes down to you can get really good performance without a lot of horrible bugs. And in the end, you can do more than you were doing before. Right? And that's true regardless kind of where you come from. If you're someone who's been hacking with C++ for a long time, I think that using Rust can help you do the same kinds of things you're doing, but then do some other things you were afraid to do because you would have had to teach other people how it worked or remember yourself how it worked in a little while, and it's hard to maintain. But if you are using higher level languages, you can eliminate performance bottlenecks and do things that those languages can't really support. So I like this quote. Rust is in use now in production in a lot of companies. One of them is NPM. They make Node.js. You've probably heard of it. And I like this quote from their CTO, where she said that she likes Rust because it's just boring, right? In other words, nobody ever wakes her up in the middle of the night and says, hey, our Rust service is out. They wake her up for other services, but the Rust ones tend to be reliable. And I think that's because of the orientation of the language in general. All right, so enough. I've sold you pretty hard on Rust. Let me now teach you a little bit about it in more depth. This is the outline of my talk. I'm going to start and cover kind of Rust's design. And then I'm going to talk about some experiences of people using Rust in production and how they used it and what for. And finally, I'll talk a little bit about the Rust community, because that's kind of our secret sauce. So Rust is an open source project. We are supported by Mozilla, a lot of us, but there's also a lot of other companies and just volunteers and so forth involved. And we try to innovate not only kind of in this technical area, but also in having a really welcoming and empowering community. So I'll talk about that. All right, so let's go back to the design of Rust. When Rust was first being designed at Mozilla, we kind of wanted to overcome this problem we had. We have millions of lines of C++ code, and there are some kind of designs we couldn't do, right? So this was a sign that was hanging, I think it's still there, I don't know, in Mozilla's offices for a while. And it said, you must be like this tall, right? Like 12 feet tall in order to add threads into Firefox. Because anytime we tried, it didn't go well. And we wanted a language that would let us do that. Now, most languages that aim to make threading safer, and there are many, take a kind of simplistic approach, in my opinion. Right, so if you have something like Erlang or something like Haskell, what they try to do is to eliminate data races by taking a radical simplification. Because a data race is this problem you have where you have two threads of execution running in parallel. They share access to some piece of memory, right? Some object, some state, and one of them at least is mutating it, and the other one is reading from it, and they're not coordinating. And then the result is kind of undefined because it just depends on which one happens to go first or if they're running at the same time. And the compiler will do all kinds of things, or the computer. And so what most people do is say, well, we can solve data races if we just eliminate one of these three ingredients. Like maybe we say, well, if you just don't use threads at all, then you don't have data races because everything is ordered. Okay, that's true. Or if you never change anything, if you just make new things all the time, like in Haskell, then it's true. You don't have data races, but then you have to overcome the kind of performance limitations of that. And similarly, if you never share any memory, you just use messages, like in Erlang or Elixir or something, then it's also true that you don't have data races. However, again, there's a performance cost. There are times when sharing things is very efficient, and it's what you want. So what Rust tries to do is, we support, you don't force you to use any of those three things, but what we do prevent you from doing is using sharing and mutation at the same time, right? So you can have sharing and you can have mutation, but you can't have them both. And I'm going to show you how we do that. And I should add one thing, I'll come to it later. I'm somewhat simplifying. You can have them both also, but you have to do extra steps. But mostly we try to avoid sharing and mutation. And the way we do it is by this ownership and borrowing scheme. And this is kind of the secret sauce of Rust. It's the thing that's most different about it from other languages. And it's what enables us to not have a garbage collector or not require a garbage collector and so forth. So the idea is that we're going to identify three patterns for working with values in Rust. Three ways that you use data. And your code is going to declare which one it's doing. The first one, the most common is called ownership. And I want to add here, this is some Rust code, very simple code, and I'm going to use it to explain the ideas of ownership. And I'm going to enlist the support of these drawings. Now, when I was preparing this talk, my daughter, who's 6 years old, said, "Daddy, can I help you make the talk?" And I was kind of stumped for a while. I was like, But then I had the idea to have her draw. So my talk got like 10x better now. These are my daughter's drawings. And the idea is, in Rust, so we're starting out with this function on the left side, and we see some bits of Rust syntax here, right? Like fn main, that declares the main function where program execution begins. And let apple is declaring a variable called apple. And when we say equals apple new, what's going to happen is new is a method. It's not a keyword in Rust, but it traditionally makes a new value. We're going to create an apple. And at this point, only one person has access to this apple, right? The main function, or one function, I guess, because it just made it. It's fresh. Nobody else knows about it yet, right? And so we say in Rust then that this function owns the apple. It has unique access to it. And next, we're going to call this function eat. And this is where things take a little bit of a turn. Because in Rust, when you declare a function eat that takes a value of type apple, what that means is that function wants ownership of the apple. It wants to be the only one with access to that apple. That makes sense. If you're going to eat it, you don't want other people trying to use it, right? So on the other side, when we call a function and we just say apple, like this, we're giving ownership away. So when we have this other function here, and this was my favorite drawing, by the way. This is awesome. So what happens is, logically, sort of, ownership of the apple goes from the main function to the eat function, right? And now it has a new owner, and main has nothing to do with it anymore. So now the eat function has an apple, it can execute, and when it's done, it returns, and at this point, remember, we don't have a garbage collector, so we have to figure out when do we free memory. Well, we use the C++ scheme, basically. When you return anything that you own, that you haven't given away, you drop or free, right? So at this point, we'll free the apple. The memory gets reused, and we're done. And now we come back. And now you might ask yourself, okay, we gave away the apple. What happens if I try to call eat again with this apple that I gave away? And the answer is, the program will not compile. The compiler tracks what you have and what you don't have. And if you try to use something you don't have, it tells you that you can't do that, right? So that's ownership, right? And now let's do a slightly more complicated example, because in this one we just had two functions. I want to have some more sides to ownership. So here I have the same function, but I'm going to create not only an apple, but a bag, which is a vector, right? An array, like a collection. And I'm going to take this bag, and you see I declared it as mutable. In Rust, when you have a local variable, if you're going to make changes to it and mutate it, you declare it as mute so that your readers can see that. Right? It kind of helps to make the code more clear. And I'm going to push something into the bag, my apple. And here, just like before, I'm giving ownership of the apple away, and I'm giving it to the bag. So now I own the bag, and the bag owns the apple. Right? And we could push some more things into the bag, like here. We'll make a new apple and put it directly in. And then I can call this deliver function. And just like before, deliver takes a vector of apples. That's what that syntax means. It's a generic syntax. And it takes ownership of the whole vector. Right? So when we call, our function comes back, and we give the whole vector over. And now they're owning the whole vector, and we have nothing to do with it or its contents. Right? They're all gone. And just like before, when this function returns, it's going to free the vector, and the vector is going to free the things that it owns, and so it all goes away. So this is what manual memory management feels like in Rust. If you've heard this term, and you've written C code, you're thinking of like malloc and free or new and delete from C++. It's not like that in Rust, right? It kind of feels invisible. It feels almost like a garbage collected language. You just make things, and then they go away when you return. Right? But we're tracking all the time who owns it at any point, so we know who is the job of freeing it. Okay, so that's ownership. The next thing I'm talking about now is borrowing. So if the only thing you could do, well, let me rephrase it. Normally when you call a function, you may not need it to take ownership of the data. You might just want it to use the data for a little while. Right? And we call that borrowing. So imagine here we have a function. This is the same vector with apples and everything. But my function is just going to read this and figure out the total weight of all the apples. So it's going to like figure out how much they weigh, right? And to say that, what we say is, you see the ampersand in front? That means that the type of this is a reference to a vector of apples, meaning we're borrowing this vector from the caller. And on the other side, we don't pass bag, we pass ampersand bag. So we're loaning it out. So what's going to happen at runtime, oh, one last thing. And it's going to, this arrow, just in case you're curious, we're returning a 32-bit integer. That's what that means. So we're going to sum up the weight and return a number. Now what happens at runtime is we don't give ownership of the bag away. Instead, we borrow it. We just pass a pointer, and it can use it, but it stays owned by the original function. Right? And that means it can execute. And now, this kind of just ampersand, these are called shared references. And I call them shared references because you can have many, many copies of them. So this is where the sharing or aliasing comes in. We can have many ways, different names for the same data. So we can already see it here. There's the bag in the caller, and then there's this bag in the callee, and they both talk about the same vector. And maybe we have vectors at the individual apples also. That's okay. And when we're done, we only borrowed the data, so nothing gets freed when we return, right? And that means we can keep going on and using the bag after. Okay, so that's sharing. But you remember I said that we don't want to have sharing and mutation at the same time. Well, this is where it gets tricky. This is sort of the part of Rust where that comes up. Because the idea of Rust is mutability, meaning the ability to make changes, is not a binary thing. It's not on or off. It's something that depends on where you are in the code and what is borrowed at that point. Right, so when we made this is the similar example, right? When we make the bag, we declared it to be mutable, and that means initially, yes, we can push things on it and make changes to it because it's declared as mutable. But here, when we make a shared reference, or when we borrow it, now it becomes frozen, and we can't change it anymore. And what happens is the compiler will analyze and see how long that reference is going to be used. And the idea is it's frozen until you're finished with that reference, right? Because that's the point where it's shared. So we now have two names to reach the bag. We can use the name bag, and we can use the name R. And they're both the same data. So it's shared across two different names. It's frozen. That means we can call bag.len. We can get the length of the bag. That doesn't mutate anything. That's perfectly fine. But we can't call bag.push because it's borrowed. And we can't call r.push. This is also the bag, but by another name, because we can't ever mutate with a shared reference. So what happens effectively is while it's borrowed, the data is immutable. Nobody can change it. But after the borrow is done, when you stopped using the reference, now it's okay to make changes again. So we started out mutable, we got frozen, and then unfrozen. And now all of this is how the compiler thinks about your code. Nothing's happening at runtime, right? There's no cost to this at runtime. We're just checking that you use things in this pattern. And if you do, we know you will not have the kind of problems I talked about earlier. So that's shared references. The last thing is kind of a twist on that called mutable references, and then these are the three patterns. All right, so a mutable reference, it's like a shared reference. You're not taking ownership of the data, you're borrowing it, but now you're having the ability to mutate. And we'll see that comes with slightly different rules, right? So just like before, we can start out being able to mutate the bag. But here, we make a mutable reference, &mute. And what that means is, just like before, we're going to figure out the range of code in which that reference is used, but now, instead of freezing the bag and saying it's immutable, what we do is we say it's still mutable, but the only way to use it is through the R reference. So I can't use this original name, bag, anywhere in that scope. Right, so right here, I can't even read the length of the bag through the variable bag. But I can use the reference, R. That's okay. And I can mutate it or read it or whatever I want. So I've kind of borrowed the right to use that value for a while. This is like, I think this is very analogous to, say, something in a library. If you borrow a book from a library, the library still owns the book, but nobody else can use that book until you're done with it. Same here, when R accesses the bag, no one else can use it until R is finished, right? Okay. And now, once R is done, we go back to the normal state. So these are the three rules. Now, what I'm going to show you now is how those three rules, we actually designed them for sequential code. When we were first working with it, we were trying to prevent those crashes that garbage collectors normally prevent. But then we realized the same three rules apply to parallel execution and to a whole bunch of other scenarios. So this is kind of what makes Rust work, is that we take those ownership rules and we use them to build a bunch of different concepts on top. So let me show you how it applies to parallelism. Our observation is there are sort of two problems when you're writing parallel code. The first one is you have to have a good runtime. You have to make it like a good way to launch threads and do all that sort of thing. And that's a relatively easy problem, or at least a relatively well understood problem, right? But so we can have, for example, in the language Go, we have this really nice, super fast runtime that lets you launch up Go routines and send messages between them with these channels, and it's very well optimized. And that's really cool. But that's only one problem, building that runtime. There's another problem which is somewhat harder, or at least there aren't so many good solutions for, which is how do we make people use that runtime correctly, right? So this is an example of some Go code. And you see it creates a map in the first few lines. And then it populates the map with a key, and then it sends it over a channel. Right? And now the problem is, the idea is probably supposed to be, I've sent this map over the channel, some other thread or Go routine is going to read it and use it, and I'm not supposed to touch it anymore. That's the whole idea. I sent the memory away. But nothing actually stops me from doing that. Right? I can go do it if I want to. And now I've created a potential for a data race. Depending how the scheduler works, this might or might not cause a problem with my program. So, and I want to emphasize something. I'm not picking on Go. This problem is kind of omnipresent. Also occurs in Java and almost every language except for research languages and Rust. Right? And so why doesn't it happen in Rust? How can we stop this? Well, it turns out ownership and borrowing kind of do the job for us. So here's the code that you saw from Go, but in Rust, equivalent code. I make a hash map, a hash table. I insert some data, and then I call channel.send. Now, how do we define this send method? Well, this is what methods look like in Rust. So just a brief detour. You first begin with this impl, which stands for implementation, and you can then add methods to a type. So here we're adding methods to the type channel of T. So T is whatever kind of data goes over this channel. It could be anything. And if you look at the argument to the send method, you see that it just has T. That means I want to own the value T. I want unique access to that data. Nobody else can use it. So now when we call, we gave ownership of the map away. And just like we saw with the apple, after you give it away, you can't use it anymore. Right? So if we then go try to use the value M, we're going to get a compilation error. So our code will never run. Okay, so ownership and message passing are like a perfect match, right? You don't even need borrowing, actually. But there are other ways to write parallel programs. One of the things that's tricky about parallel programming, actually, is you can get enormous speedups, but there are a variety of paradigms, right? And you have to find the right one for your problem. And so Rust is aiming to support not just message passing and not just actors or what have you, but everything, all these different paradigms, because you never know which one your application will need. And one of them that's very common is something called fork join. And the idea here is you have some sequential loop. You have something you were doing sequentially, and you want to kind of split off and do it in parallel, and then when they're all done, keep going. Right? So let me give you an example. This is a function that loads a bunch of images. It starts out by taking a vector called an array, called paths, which will be just a list of paths in the file system, right? File names. And this ampersand is just saying, I borrowed this list from my caller. I'm just going to use it. I don't own it, right? And what we're going to do is we're going to call paths.iter, which creates an iterator. Now, Rust iterators are kind of lazy, so they don't do anything until the very last statement, essentially. But here we made an iterator, and we're going to call map. And that's saying, for each of these paths, invoke this closure, that function, right? And that closure is going to load the image. And now, when we call collect, this is what makes the iterator actually execute. And it will call that closure on each thing and load the image and create a vector. And that vector gets returned. So it's going to execute one at a time, right? This, by the way, is also my daughter, but when she was born. And so that's okay. We just loaded these pictures one at a time, but there's no reason to do that one at a time, right? We might like to do that in parallel because there are not interactions between them. So what we could do to do that is we can use this third-party library called Rayon. And I want to show that it's a third-party library because that's part of Rust's philosophy, is that the core language is relatively small, and we build all the cool stuff, all the toys and gizmos in libraries, so that you also can build your favorite gizmo, right? Whatever you need. We don't try to make the language itself do everything. So this library, Rayon, what it does is it adds a concept of a parallel iterator. And everything is the same, but I changed the first line. And now, when we call collect, they're all going to load in parallel with one another, right? So this is cool. And you have similar libraries in many languages. Right? This comes back to my observation. Building that runtime, building that library isn't actually that hard. But what's kind of hard is preventing you from screwing it up. So if we go back to that example of loading the images, I made one change. I added 2 lines. I added a counter of how many JPEGs we saw as we went through, because maybe they have different formats. I don't know. Right? And I'm testing, does the file name end in .jpg? Then I increment the counter. Seems fine. In a sequential loop, this would be fine. But in parallel, this is not okay. And here's why. You have some counter here. It has 0 in it. And now you have 2 threads. Right? And you can see these are my lame, before my daughter got a hold of my pictures, that's what they look like. And so when they go to add 1 to this counter, the way they do it is in steps. First, they read the current value. Okay, so maybe they're both running at the same time, actually. So they both read 0. Then they add 1 to what they just read. So they both get 1. And now they write back, right? And so now you're only going to get 1, but actually you loaded 2 pictures. Both threads loaded a picture. So that's not good. And in fact, you might not even get 1. You can just get total gibberish if you're unlucky. But so what this is, well, oops. So the key thing here is that this kind of problem this is exactly the worst kind of data race, actually, in some sense, because the only result probably is that your count is going to be slightly wrong. Right? So if you had 10,056 images, your count might be 10,052. And are you going to notice that it's wrong? Probably not. Like if you knew how many there were, you wouldn't have written the stupid program, right? So luckily, Rust would not accept this program. And let me explain why. So this is the same code, but in a slightly different format. I've pulled out the closure that's running on each thread down below. And the idea is, even though you wrote the closure once, we know there's going to be 2 copies of it running. Right? And each one is going to access this counter JPEGs that they're incrementing. And to do that, they're actually borrowing it. This is borrowing, but with a fancier syntax. So conceptually, they have a mutable reference to this counter, and they're going to change it. And there are 2 of them, right? And each one has a mutable reference. But we said you can't have a mutable reference and sharing. Mutable references have to be unique. So what happens is the compiler sees that this closure might potentially run in parallel. The pariter function declares that. And it says, if you're going to run in parallel, you can only use shared references. You can't use mutable references. So this code does not compile, right? And you remember the blog post way back in the beginning of the talk, I had a blog post, and it said, the Rust compiler just saved me from a nasty threading bug. This is exactly what that blog post was talking about. It was a bug like this. So this happens in real code very easily when you're not paying attention, right? So now we saw that using borrowing and fork join, we get a really nice match. And there's a whole bunch of other parallel stuff I won't talk about, but you can do all these other kinds of things too, right, in Rust. Okay, so I want to take one little detour to show you something under the covers and why I've been basically lying to you this whole time. Because I told you that Rust prevents all these kinds of bugs, that Rust is super safe, and yet, and I also, well, I didn't actually tell you this, but I should have told you if I'd remembered my script correctly, that one of the other things about Rust is that you don't need any other languages to do it, right? Like our entire standard library, for example, is written in Rust. There's no C in Rust, just some assembly here and there. And how do we do that? The way we do that is by a trick called unsafe code, right? And so the idea is we wanted Rust to be this extensible language where the core language is fairly small. And it just has this idea of ownership and borrowing. And then we have these libraries that kind of build on top or grow on top, I guess, that do things like parallelism or interacting with the file system or managing memory via reference counting, stuff like that. And if you actually want to safely, in a type system, describe all those things, your type system gets super big and super complicated, right? So what we did was we kept the type system simple, but we gave an escape hatch. You can write this kind of code that's called unsafe code. And basically it lets you write sort of C code, but in Rust syntax. Right? So you say unsafe, and inside here you're telling the compiler, hey, I got this. I'm checking it, it's fine, you can just look away and pretend you don't see it, right? It's cool. And the idea is you're not supposed to just throw these blocks wherever the compiler is irritating you. You're supposed to put them inside of a nice function that has a nice interface, like the parallel iterator, for example, where it looks very clean and your consumers don't have to worry about it. Right? So you can think of this, it's analogous to if you had some Ruby code and you wrote a C plugin, right? Ruby code doesn't have to know that it's written in C. It just goes faster, right? Same idea. So you might wonder how much unsafe code there is in practice. I wondered that too. And I'm giving you some numbers from something I'm going to talk about in a little bit. This is an extension to Firefox that uses Rust. But what we found here, we did some measurements of how many lines of code and so on use unsafe. And at first I was a little disappointed because I got 35% as the number, and that sounded like a lot. Especially because in the code I write, I basically never write unsafe. So I don't know why it would be so much. So we went looking, and it turned out that what's really happening is you can divide that project into two parts. First, there's the interesting stuff that does, like, this is a parallel CSS layout algorithm. And then there's this other crap, which is the FFI bindings, where it interacts with C++. And that is kind of inherently unsafe, because you're telling the Rust compiler, here's all these C data structures that you don't understand. This is what they look like. Right? And so really the number that's most interesting is actually 2%. And even that's a little exaggerated because of some stuff they did. So basically, in a really complex, really low-level systems project, we still only had about 2% unsafe code. Right? And most code just doesn't have unsafe at all. So this is sort of something you need to be aware of, but hopefully don't interact with as a Rust user. All right, so I want to talk about one more application of Rust, which is integrating into other languages. And I'm going to go a little bit quick through it, but I wanted everyone to know that it's possible. So there are a bunch of really cool projects out there for integrating with different runtimes in different languages. There's one for Ruby called Helix, one for Node.js called Neon, and some CPython ones. And what they share in common is that they aim to, they aim to sort of let you extend the language in a safe way. So if you have, I'm going to skip over these slides because I have a little less time than I thought I did. And just tell you that they're out there, and if you use them, you can have some pretty big effects. So this is an example of a crypto calculation. So Wire is a desktop app that uses Node.js over Electron, and they had some cryptography stuff they were doing, and they wound up using Rust to do it. And what they found was they were able to get really big speedups, basically because in the Rust code they could use parallel threads. Right? So JavaScript doesn't really support parallel threads that well, but they could write a native Rust plugin and very easily parallelize some of their computation. In fact, they said up to 141 times faster. And some things like Helix actually uses Rust macro system. These are macros. I won't talk about them in depth, but they're a way for us to extend Rust syntax, basically. So you can write kind of nice looking like Ruby declarations, but inside there is Rust code. And it generates all the bindings and stuff for you that makes that work. All right, so let me talk a little bit about Rust in production. There are three interesting cases. I'm going to talk a little bit about the first two today, but if you're interested, we also have white papers online that talk in depth about Tilde and Chucklefish, Chucklefish is a game company. So Mozilla, I would call us pretty experienced system developers. We've written a lot of C++ code. But we had this problem, which is if you're doing CSS layout, everybody knows, everybody who builds a web browser anyway, that CSS conceptually can be parallelized very easily because the styles for one node have no relation to the styles of its siblings. So you can process all the children of a node in parallel. Right? And this has been well known. There was a Bugzilla bug first reported 7 years ago that said, let's do this. This would get us a good performance win. And if you read that bug, you'll find that they tried in C++ twice, and it never worked because it was too hard to get all the data races, to get everything else out. Right? So recently, we did do this in the Quantum release, and we did it in Rust. Right? And this is what I meant about Popeye spinach. Doing it in Rust made it feasible to do something we couldn't do in C++, despite having, all C++ expert team, right? Because we were able to work out the data races and so on. And it's not just Rust. They did a lot of cool other innovative stuff. But this Rust was a key ingredient here. So this is also a story about gradual adoption. Because if you look at all of Firefox, we've written these two parts in Rust, the CSS layout and this other thing called the renderer. But all the rest of it is still C++, right? So you don't have to convert your entire code base to Rust to use it. You just have to find good parts and extract them and convert them independently. So that was an example of Mozilla putting Rust to use. Another example comes from Tilda. Tilda is a company, and they're like a Ruby on Rails specialist and shop. They do a bunch of things, actually. Full stack is maybe the best description, right? Kind of generalists. And one of the things they do is build this Skylight performance monitoring software. And what it does is it takes your Ruby on Rails installation and tells you where you're using memory, where you're using CPU, and so forth. And they were using it was all written in Ruby, but they were having some problems. They were using too much memory, and they were starting to interfere with the Ruby on Rails installations they were supposed to be monitoring, right? And that's a problem. So the first thing they did was they tried to rewrite their Ruby code to be faster. So they did all the things that Rust is telling you don't have to do. Like they took all the closures out, and they took all the fancy, nice Ruby features and kind of wrote it in really low-level Ruby code. And it wasn't good enough, right? Moreover, not only was it not good enough, it's hard to maintain that sort of code because you get a new Ruby developer in there, and they don't know all the tricks, and they start using features they're not supposed to use, and everything goes bad. And if you've written JavaScript, highly optimized JavaScript, you'll know about this too, right? Targeting like the V8 JIT, exactly how it works. Small changes have big effects. So this is a problem. So then they tried it in C++, but that wasn't a good fit for their team because they didn't have a lot of C++ experts. And to really use C++ correctly, you have to have the right experience, basically. Right? And the main thing is, if their application should crash, if you put that in your Ruby on Rails installation and your website goes down, you can bet they're not going to get a return call, right? It's over. So what they did was they wrote it in Rust, and it worked pretty well for them. And in fact, so they had this problem before they were using 100 megabytes of memory frequently, and at that point they would reboot their program, so they probably would have used more, but they just kept killing it. And now they use about 8 megabytes, and they also added all these new features, and still they use 8 megabytes, right? Because we're not using a garbage collector, we're using the Rust scheme, and it just stays flat. Okay, so those are some cases of Rust in production. I want to talk a little bit about how Rust manages its community processes, how our development works, and so forth. And in my dream world, some of you got excited enough about Rust that maybe after this you'll come and check out and try to join the community and contribute back, help us with the compiler or the libraries or the other things, right? So I said that Rust is an open source project, but we don't just mean the code. We try to involve the community in all of the decision making as well. And so this begins in the beginning of the year. We have a roadmap discussion where we try to figure out what are the biggest problems we're going to do and try to tackle this year. So for example, our 2018 roadmap, we're kind of continuing a focus that we've had now for about a year on improving the type system and so on to make language more ergonomic, meaning easier to use, basically, but in a complex, yes, easier to use and get things done, more productive. And we're trying to make a big release, right? And that was something we laid out in this roadmap. And then once we've done that, if you want to make a change to the Rust language or something else, then you can make smaller proposals in the form of RFCs, request for comment, right? And basically you can write up a feature. Ideally it should fit into the roadmap somehow, though sometimes they don't if they're small enough, and propose it, and people will discuss it, and eventually a decision is reached, whether to do it or not to do it. And this is all done publicly, and it's the same for, I should add, any feature. So I've been working on Rust for 6 years or something, but if I want to add a feature, I also write an RFC. Right? It's the same process for everyone. And the teams that make the decisions on those RFCs, we have been growing quite a few now. they're all drawn from people who've been working on Rust or contributing to Rust, right? So there are about 7 Mozilla employees, but there are like 60 or even 100 people, I think, on these teams now, and the rest of them come from other places. So we operate kind of on a consensus basis. So for example, if there's a new language change, the language team has to reach a consensus that everyone agrees this is a good change, and then we can move forward. We also have these things called domain working groups. These are a relatively new innovation, where we're having, basically we want to make Rust work better for something like web services or WebAssembly or CLI applications. And so we have people focusing, exploring those areas and coming up with suggestions on how we can make improvements there, right? And they're not part of the Rust teams, so to speak. They're like an orthogonal thing. So it's a lightweight way to get involved if you have an opinion about something like that. And finally, I would just say that we make a big effort, I think, we see Rust as appealing, as I said, both to experienced system developers, but also people who don't have experience. And I think both of those camps have a lot to offer one another, right? A lot of skills that the other one lacks. And so we try to have a welcoming and opening community for both, so that we can exchange and learn from each other. And that's really important to us. So this drawing came from Julia Evans' keynote at RustConf a couple years ago, and I just love it. I think that's exactly the spirit that we're shooting for. So thank you all very much. Well, oh wait, before I say that, one last thing. If you're interested in learning Rust, you can find many books now. There are more and more all the time. There's also some screencasts that I've made if you like my style. If you don't, it's okay. I won't be offended. But you can find others here at the Rust Learning repository. So I encourage you all to check it out, and now I'm happy to take questions. And thank you for your attention. Oh, yep. There is. The Go community, how do I see the Go and the Rust communities in terms of overlap? Is that what you're asking?
Yes. How do the Go and Rust communities overlap?
That's an interesting question. I don't actually know. I think there definitely are a lot of people who use both Go and Rust and have opinions, one way or the other. But I think I'll answer a slightly different question, if you will. One thing I've observed a lot, I think Go and Rust have a sort of intersection. We're very different languages, but we target an overlapping set of use cases. And one pattern I've seen a lot is that you will see kind of big Go installations supported also by kernels of Rust code. So kind of like you can use Rust code to take some hotspot in your Ruby installation and make it faster. The same applies to Go, essentially, or to save memory and so on. That's something that, for example, Dropbox has done. They rewrote all of their file storing software, the core of it in Rust, and then the rest is like Go processes. So I think there's a lot of friendly cooperation.
Quem quiser perguntar em português, eu posso traduzir também, tá? Se não você...
Hi. Is there any working group on IoT, taking Rust to IoT stuff, like Arduino?
Like IoT, you say IoT?
Yes.
Okay, so the question is there a domain group for IoT? I think that would fit under the embedded domain group. A lot of the people in that group are doing IoT, as far as I know. Yeah.
So his question is if you can elaborate a little bit more about the dependency management system, the package system.
I see. Okay, so yes, our package management system is called Cargo. It's based closely on, I think it's Bundler in the Ruby. In fact, I think it was designed by, I think Yehuda Katz designed both of them. But the idea is that you have a file where you specify your dependencies and you give the version number, like the semver compatible version, a 1.0 or whatever. And then that will go against our database, download, find the right version that works across all your packages, download it. We also have a lock file that records exactly which versions you use so that you can have repeatable builds. And we're working now on generalizing it. It's still in progress, but like there are ways to run your own servers if, for example, your company doesn't want to use the global one and so on.
Can you tell us a little bit about tools like compilers, debuggers, and jitters, something like that?
Yes, the tools. We have a lot of tools. We have a whole team doing tools. But I would say, one of the big focuses of the last couple of years has been getting good IDE support in particular. And VS Code is sort of the primary. We have a tool called the Rust language service that fits into VS Code, but it can also be used from other editors. And there's also an IntelliJ plugin for Rust. So on the IDE front, that's what's there. In the debuggers, you can also use traditional like GDB or LLDB, these more traditional C-level debuggers. And that's something we're still it works definitely. It's always under improvement to get better debug info. And we're actually working now on getting Rust into the dwarf standard so that will work even better. And in terms of other tooling, usually what happens a lot is that Rust generates very C-like executables. So you can apply a lot of the C tooling infrastructure, like prof on Linux for doing profiling, or tracking which lines are executed and so on, code coverage. So that's kind of, we tend to piggyback on C tooling, at least until we have our own on top.
Última pergunta.
In high-performance computing, it's very common to parallelize code using OpenP and PI, and speed up, it's very good. But is there a benchmark comparing Rust, or Rust can reach these speed up like C++ using OpenP and PI?
So is there a benchmark that compares Rust to OpenMP? I'm not aware of anyone who's specifically compared them like in a thorough way, but certainly we can achieve similar speedups. Let me say that like the Rayon library, for example, I have seen a number of people do comparisons, none that have been publicly announced that I know of. And Rayon always does as good or better than those other libraries for reasons. But I don't think what I don't think anyone has done is taken like standard OpenMP benchmarks and ported them and compared them. That would be an interesting project to do.
All right. Thank you very much. Excellent talk.